to Chapter 2, Biomechanics of Resistance Exercise. Today we will explore the mechanical principles that govern human movement and force production during strength training. Understanding these physics-based concepts is essential for maximizing athletic performance and minimizing injury risks. Let's look at our core goals for the first half of the session. By the end of this chapter, you should be able to identify key components of our skeletal musculature, distinguish between the three classes of levers in the body, map out primary anatomical movements, and mathematically calculate linear and rotational work and power. Continuing our objectives, we will also dive into the physiological and biomechanical factors that dictate human strength and power. We will evaluate how different exercise devices distribute resistive forces and conclude with a look at joint biomechanics to keep exercises safe and effective. To build a solid foundation, let's define biomechanics. Simply put, it is the study of how internal forces like muscle contractions and external forces like gravity or a barbell interact within the human structural framework to create movement. Our bones act as levers, but they require the skeletal musculature to move. When referencing muscle attachments, we use two terms: origin, which is the proximal attachment closer to the center of the body, and insertion, which is the distal attachment farther away. Muscles rarely work in isolation. The agonist or prime mover handles the primary work of the movement. The antagonist opposes or slows down the movement to protect joints. Finally, synergists act as helper muscles to stabilize the movement or assist indirectly. Most movements in sports and weight training happen via bony levers. A lever is simply a rigid or semi-rigid body. When an off-center force is applied to it relative to its pivot point, it rotates and transmits that force against a resistance. Let's establish our variables for lever mechanics. Fa is the force applied to the lever, and MAF is its corresponding moment arm, the perpendicular distance to the fulcrum. Conversely, Fr represents the resistive force, and MRF is the moment arm of that resistance. Visualizing a diagram, notice how the fulcrum sits in the middle, separating the resistance on the left from the applied force on the right. The length of the moment arms, MRF and MAF, directly dictates how much effort is required to move the resistance. Mechanical advantage is the mathematical ratio of the applied force's moment arm to the resistive force's moment arm. A ratio greater than 1 means you can lift a heavy load using less muscle force than the load itself. If it's less than 1, the muscle must exert a force greater than the actual weight being lifted. A first-class lever positions the fulcrum right in the middle, with a muscle force and resistive force acting on opposite sides. A classic everyday example of this is a playground seesaw. Looking at figure 2.2, let's calculate the mechanical advantage here. The muscle moment arm, MM, is 5 centimeters, and the resistive moment arm, MR, is 40 centimeters. Dividing 5 by 40 gives us 0.125. Because this value is well below 1, the muscle operates at a severe mechanical disadvantage. This anatomical graphic highlights the tricep extension or a head-neck balance scenario. The elbow joint, acting as the fulcrum 0, sits between the force of the muscle pull Fm and the external resistance Fr. In a second-class lever, both forces act on the same side of the fulcrum, but the muscle force boasts a longer moment arm than the resistive force. The structural setup guarantees a mechanical advantage, meaning the muscle force required is always smaller than the resistive load. Perfect example of a second-class lever in exercise is a standing heel race. When you lift your heels, the ball of your foot serves as the fulcrum O. Because your calf muscle attaches further back, the heel, its moment arm MM, is longer than the body weight resistance arm MR. Examine the arrows in this foot diagram. Notice that the upward muscle force Fm is located further away from the pivot point at the toes O than the downward pull of the gravity body weight Fr. This is the only lever class that gives our muscles an absolute mechanical force advantage. A third-class lever also places both forces on the same side of the fulcrum, but this time the muscle force acts through a shorter moment arm. The mechanical advantage drops below 1, requiring the muscle to output massive amounts of force just to counter a relatively light weight. Think of the classic bicep curl. Your elbow is the fulcrum, the dumbbell in your hands is the resistive FR, and the biceps tendon inserts just below the elbow FM. Because that muscle moment arm MM is tiny compared to the forearm's length MR, your biceps must pull with incredible force. This diagram clearly illustrates the third-class lever system. Observe how close the blue muscle force arrow FM is to the elbow joint fulcrum. Most structural setups in the human body are third-class levers. Why do we have a kneecap? The patella prevents the quadriceps tendon from hugging the knee joint too closely. By pushing the tendon outward, it increases the distance from the knee's axis of rotation, lengthening the moment arm and boosting our mechanical lifting advantage. In this anatomical view, notice how the patella lifts the quadriceps tendon away from the femur and tibia. This expansion holds the line of action further from the axis of rotation, maximizing joint torque production. If the patella is removed or absent, look at how the tendon falls directly flat against the joint center. This severely shortens the moment arm, forcing the quadriceps to work significantly harder to produce the exact same amount of leg extension. Mechanical leverage is dynamic, not static. As a joint goes through a full range of motion, the perpendicular distance from the joint axis to the tendon's line of action continuously changes. When the moment arm shrinks, our mechanical advantage drops. Follow the length of the moment arm M across these 5 arm positions. Notice that M peaks when the elbow hits roughly 90 degrees. At the very start or end of the movement, M is brief, creating the natural sticking points you experience when lifting. It isn't just the muscle's moment arm that changes. The resistance's moment arm changes too. When lifting a free weight, gravity pulls straight down. The resistive torque is entirely determined by the horizontal distance from that weight to your joint pivot point. This arc graphic visualizes why bicep curl feels hardest right in the middle. When the forearm is perfectly parallel to the floor, the horizontal moment arm M reaches its maximum length, producing the highest resistive torque against your muscle. Here's a vital takeaway. Because our bodies rely heavily on third-class levers, most of our skeletal muscles operate at a severe mechanical disadvantage. This means the internal forces generated within our muscles and tendons are vastly higher than the actual weight held in our hands or feet. Genetic differences play a massive role in lifting potential. Individuals whose tendons insert further away from the joint center have longer moment arms, allowing them to naturally lift heavier weights. However, the structural advantage comes with a trade-off, a noticeable loss in maximum movement speed. Let's break down the speed versus power trade-off. A tendon inserted closer to the joint, configuration A, creates a shorter moment arm, produces more joint rotation per unit of muscle contraction, translating to faster movement. Configuration B creates massive torque but moves slower. In this diagram, the tendon inserts close to the elbow joint. Watch how a slight contraction creates a large sweep in joint angle, moving from 37 degrees to 22 degrees, favoring high velocity movements like throwing or sprinting. Now look at the distal insertion further down the bone. For the exact same amount of muscle shortening, the joint rotates significantly less, 34 degrees to 17.5 degrees. It moves slower, but the mechanical leverage is far superior for grinding out heavy weights. To analyze human movement properly, we use the standard anatomical position as our reference point. We divide movements into 3 distinct structural planes: the sagittal plane, left and right halves, the frontal plane, front and back halves, and the transverse plane, upper and lower halves. Let's look at the complete visual breakdown of how these primary movement planes intersect across a human model. We can use this slide as a clear visual guide. Note that the vertical blue sheet represents the sagittal plane. The vertical purple sheet maps the frontal plane, and the horizontal purple slice shows the transverse plane. Let's transition from theory to practical application. Every strength exercise and sports movement can be categorized into one of these specific planes. Let's review the upcoming matrix mapping common movements. This chart displays upper body joint actions. For example, wrist curls and bicep curls occur cleanly within the sagittal plane. Dumbbell flies and shoulder internal external rotations belong to the transverse plane. Front shoulder raises sit in the sagittal plane, while lateral raises fit into the frontal plane. Moving down the body, we see lower back sit-ups and stiff leg deadlifts running through the sagittal plane. Side bends occur in the frontal plane. Leg extensions and leg curls are strictly sagittal, while hip abduction and adduction machine movements are frontal actions. Let's define our performance terms precisely. Strength is the maximum capacity to exert force at any given speed. Acceleration is the rate of change in velocity over time, tied directly to force output via Newton's second law. Force equals mass times acceleration. In physics, work is defined as force multiplied by displacement. Power introduces a time constraint. It is the rate of doing that work calculated as work divided by time. In training rooms, coaches frequently refer to power as explosive strength. Work isn't just positive, it can also be negative. Negative work occurs when a weight or external force performs work on the muscle rather than the muscle doing work on the weight. This happens explicitly during eccentric or lowering muscle actions. Because our body movements are rotational around joint axes, we must also track angular metrics. Angular displacement is the actual angle through which an object rotates. Rotational work is calculated by multiplying torque by that angular displacement. Let's clarify a common point of confusion. Strength and power both reflect force production, just at different velocities. For example, Olympic weightlifting requires much higher power output than powerlifting because Olympic lifts move heavy weights at incredibly high speeds. What dictates how much force a muscle can produce? The first factor is neural control. Your brain regulates force using recruitment, choosing how many motor units to activate, and rate coding, determining the rapid frequency at which those motor units fire. The second factor is the physical structure of the muscle fibers. Pennate muscles feature fibers that run obliquely relative to the central tendon, creating a feather-like design. The angle of pennation dictates how many fibers can pack into a given area to drive force production. The next slides will show the muscle fiber arrangements and provide an example of each. And you see that here in various parts of the body. Let's continue exploring human strength by looking at muscle length. The muscle's force capacity varies heavily based on its length during contraction. At standard resting length, actin and myosin filaments have the optimal amount of cross-bridge potential, meaning the muscle can generate its maximal force. If a muscle stretched too far, filament overlap decreases, dropping potential cross bridges. Conversely, when it is heavily contracted, filaments overlap too much, leaving no room for further cross bridge action and limiting force capability. The next slide talks about some of the things we reviewed in the first lecture regarding muscle length and actin and myosin and interaction. And these are some slides that should look familiar based on those materials. Joint angle is directly tied to muscle torque production. Because muscles pull on bones across a changing axis of rotation, the moment arm length varies through an exercise's range of motion. This dictates the amount of force required at different phases of a lift. For example, during a biceps curl, the mechanical advantage changes constantly, leading to specific sticking points where the muscle must work harder due to unfavorable leverage. So the key terms in this section are concentric muscle action, which is a muscle action in which the muscle shortens because the contractile force is greater than the resistive force. In contrast, eccentric muscle action is a muscle action in which the muscle lengthens because the contractile force is less than the resistive force. And then in further contrast, an isometric muscle action is a muscle action in which the muscle length does not change. The next slide will pull many of these concepts together to talk about the force velocity curve. And this depiction shows how the three muscle actions discussed impact torque depending on the muscle type. Also comparing these in relation to flexors and extensors. Strength to mass ratio is a critical factor when comparing athletes of different body sizes. As body size increases, body mass grows. grows at a much faster rate than the muscle strength does. This occurs because muscle strength is proportional to cross-sectional area, square dimension, whereas body mass is proportional to volume, a cube dimension. Consequently, consequently, smaller athletes routinely display a higher strength to mass ratio compared to larger athletes. This slide summarizes how body size impacts strength. If you scale up an athlete's dimensions proportionally, their weight increases faster than their ability to produce force. This explains why lighter weight class lifters can often lift multiples of their own body weight that heavyweight lifters cannot match. When designing training goals or analyzing athletic performance, always factor in this absolute versus relative strength differential. This is another key point about how strength to mass ratio impacts performance, in this case, sprinting and jumping. We'll now transition to how the body interacts with external loads. To evoke an adaptation, muscles must overcome a resistive force generated by a source outside of the body. 5 primary sources of external resistance encountered during athletic training are gravity, inertia, friction, fluid resistance, and elasticity. Each source features a distinct mechanical profile that alters the torque requirements placed on our skeletal musculature. Gravity is the most ubiquitous source of resistance in training. It pulls directly down on any object, exerting a force equal to the object's mass multiplied by local gravitational acceleration. Because gravity acts exclusively along a vertical line, the moment arm of a free weight is measured purely horizontally. Perpendicular distance from the joint pivot point to the vertical line dictates the actual resisted torque. When lifting free weights, your technique changes the horizontal distance of the load from the joint. For example, tilting the torso forward during a barbell squat moves the bar horizontally closer to the knees, but further from the hips. This decreases the resistive torque around the quadriceps while substantially increasing the torque requirements on the hip extensors and lower back. This slide reinforces the importance of proper technique. It is not just for injury prevention, but also performance. Weight stack machines isolate gravity similarly, but route the force via cables, pulleys, or cams. This configuration allows engineers to redirect the line of action, creating custom resistance curves that are difficult to reproduce with free weights. Cams can intentionally match human leverage advantages, making the exercise harder when the muscle's strongest and easier at mechanical sticking points. Let's look at the training trade-offs. Weight stack machines provide a highly controlled path, eliminate the need for stabilization, and offer rapid weight adjustments. However, free weights provide holistic whole body benefits. Free weight movements force synergistic muscles to work as stabilizers and closely replicate the balance, posture, and coordination patterns seen in real world sports and daily life. This slide shows some of those concepts that we just discussed. Inertia is an object's natural resistance changes in its state of motion. According to Newton's second law, extra force is required to accelerate or decelerate a weight beyond its static mass. When an athlete lifts a barbell explosively, the initial push requires a massive surge of muscle force to accelerate the bar, but the load becomes light or weightless near the apex due to momentum. Inertial forces can act in any direction, not just vertically. This is used in training techniques like bracketing. Bracketing involves practicing a sport movement with a slightly heavier or slightly lighter implementation than normal. Training with a lighter than normal load develops higher velocity capabilities, whereas training with a heavier load taxes force development without ruining the overall movement mechanics. Friction is a resistive force encountered when attempting to slide an object that is pressed against another surface. The maximum force of friction is determined by multiplying the normal force pushing surfaces together by the coefficient of friction. Friction-based exercise devices require high force to start moving and provide uniform resistance, but they do not change based on acceleration like inertial loads do. In daily sports setting, friction is seen when gripping a heavy barbell or climbing a rope. Some resistance training equipment uses friction belts or brake pads such as cycloergometers. A key characteristic of friction-based exercise is that it remains a constant throughout the motion regardless of speed, and it does not allow for momentum or explosive ballistic power development. Fluid resistance is the resistive force encountered by an object traveling through a liquid or gas. or by a fluid moving through an opening or past an object. This factor is dominant in sports like swimming, rowing, skiing, and sprinting. Fluid resistance machines feature a unique property. Resistance rises progressively with speed, meaning the harder and faster an athlete pushes, the greater the resistance becomes. Fluid resistance stems from two main sources, surface drag and form drag. Surface drag is caused by the friction of a fluid scraping across the outer surface of an object. Form drag results from the fluid pressing directly against the front surface of the object as it cuts through. Modifying body posture or equipment cross sections drastically shifts form drag, which is a major factor in sports biomechanics. Elasticity involves resistance generated by stretching components like springs, bands, or elastic tubing. The behavior in elastic component is defined by Hooke's law, which states the force is equal to the stiffness constant multiplied by the distance stretched. Essentially, the further you stretch the band, the greater the resistance becomes. The progressive loading profile of elastic resistance presents a unique challenge. The start of a movement, when the band is lax, the resistance is minimal. Full extension, the resistance peaks. While this can complement lifts by adding resistance at terminal lockout points, it does not match the natural force velocity or leverage curves of human muscle groups well. We'll now focus on joint biomechanics and injury prevention. While resistance training is exceptionally safe compared to contact sports, specific joints face high forces. Most human skeletal muscles operate at a severe mechanical disadvantage, meaning internal tendon and muscle forces are often much higher than the external weights being handled. The lumbar spine is the most vulnerable structure during heavy resistance exercises. Forces acting on the intervertebral discs can reach extreme levels during compound lifting movements. To protect these structures, exercises should be performed with the spine held in a neutral or moderately arched lordotic position. Rounding the back under a load causes dangerous wedging of the discs, elevating injury risks. Back injuries usually result from bad posture combined with high resistive torques. When the trunk leans too far forward, the horizontal distance from the barbell to the lumbar vertebrae increases dramatically, expanding the resistive moment arm. This forces the erector spinae muscles to contract with massive force to counteract load, pushing compression and shear forces to risky levels. The body uses a natural mechanism to protect the spine, intra-abdominal pressure. Contracting the abdominal muscles and diaphragm creates a pressurized rigid compartment in the lower torso, known as the fluid ball. This internal pressure exerts an outward force against the front of the vertebral column, supporting it from within and decreasing the deep compressive forces placed on the lumbar discs. The next slide will show us an example of what this fluid ball looks like. And so here is this visual. Athletes frequently maximize intra-abdominal pressure by using the Valsalva maneuver. This involves forcefully contracting the abdomen and chest muscles against a closed glottis, which prevents air from escaping the lungs. While this creates an incredibly rigid torso that stabilizes the spine, it also spikes blood pressure and reduces venous return to the heart, which can lead to dizziness if held too long. Weightlifting belts are a highly effective tool for improving lumbar safety when lifting heavy loads. A tight belt gives the abdominal wall a solid surface to push against, boosting an intra-abdominal pressure beyond what the body can generate alone. However, belts should be used conservatively, primarily for near maximal lifts that directly load the spine, so that the athlete's core muscles develop independently. The shoulder complex is exceptionally prone to injury due to its anatomical structure. As a multi-axial ball and socket joint, it provides the greatest range of motion in the human body, but sacrifices structural ability to do so. The shallow glenoid cavity relies heavily on the rotator cuff muscles, ligaments, and the labrum for stability, making it highly vulnerable to impingement or tearing under improper loading. To prevent shoulder injuries, athletes must maintain balanced development between the front musculature and back stabilizing muscles. Heavy pushing exercises like the bench press must be counterbalanced with row and pulling variations. Furthermore, avoiding extreme hyperextension during the overhead or wide grip lifts keeps the humeral head from shifting forward out of its safe alignment. The knee is a hinge joint that primarily handles flexion and extension in the sagittal plane. Because it sits between the two long levers, the femur and the tibia, it experiences substantial torque. The patella plays a vital role here by pushing the quadriceps tendon away from the joint axis, lengthening the moment arm, and increasing the muscle's mechanical advantage. The knee joint is subject to high patellofemoral compression forces, especially at deep flexion angles like the bottom of a full squat. To protect the knee, ensure proper patellar tracking by keeping the knees aligned with the toes, avoiding inward collapse. While knee wraps can provide passive elastic recoil to assist with lifting heavier weights, they also increase the patellofemoral friction and should be reserved for maximal attempts. To conclude Chapter 2, let's review the key rules for reducing injury risks across all joints. First, always perform thorough warm-up sets with light weights before handling working loads. Second, prioritize executing movements through a full, pain-free range of motion to build tissue tolerance. Finally, use conservative weights when introducing a new exercising, allowing the nervous system and stabilizer structures to adapt safely.